Here we are at the final session in our Unit 6 of oblique triangles. And what a nice place to be. We've done this and this and this. We worked on finding the area last time, and now problems that we actually encounter in the world. So let's take a look at some. Here is an approach we can use. Draw a picture. You're going to notice in every one of these examples we're going through, and we have quite a few of them to go through, we will draw a picture. We'll label the picture with variables. These are the variables that we're going to use in our solution. Figure out what kind of triangle you are looking at as far as what the givens are. That will determine for you whether you're going to use the law of sines or the law of cosines. Now, remember way back, and I told you that a trig student has to be persevering, very persistent. Here it is. These problems are many times multi-stage. We're going to have to work one thing after another. So you have to be somebody who can really stick with it. We can use right angle trigonometry. If you're looking for an area, you've got to determine whether you use this approach or Heron's formula. Okay, now, after you've done all that, look at what you got and determine whether or not you've answered the question. For example, I remember we were looking at an octagon, and I had found probably I didn't do that right, but I had found the area of one triangle, and I remember, at least for a moment, thinking, done. No. The question was, what is the area of the whole octagon? Put the units on, box your answer, and finally, does it make sense? We'll start with this one. This is right out of your workbook, so you can follow along here. Here's an illustration of what we're about to go over. A tree leans 7 degrees to the vertical. So here's the strictly vertical. And it's leaning right here 7 degrees. At a point 40 feet from the tree on the side closest to the lean, not away from it, but closest to it. So this is 40 feet. The angle of elevation to the top of the tree, so we're talking about this angle right here, is 24 degrees. So what have we got for information? We've got an angle and a side. That isn't enough. We need more. And we can actually figure out more, because if this is 7 degrees and we know this is a right angle, then this angle right here must be 83 degrees. That's right. And we are interested in finding how tall this tree is. Let's call that A. So this would make this A, and let's say this is B, and this is C over here. We'll put together our little chart that'll guide us when we go to figure out what we're going to do. So we've got alpha, that's 24 degrees. We've got beta, that's 83 degrees. We have not got gamma, and I guess we actually don't even care what gamma is. We could certainly figure it out though, couldn't we? Let's look at this a minute. What would gamma have to be? If we've got 24 and we add 83, we get 107, we find the difference with 180, so it's 73 degrees. Actually, calculate that pretty easily. If you got 2 of the degrees, you can figure the next one. A, which is the one we want. This is the important one to us. This is what we're looking for. What is the length of this tree? B and C, of course, we have. It's 40 feet. So looking at this, we can use the law of sines if we have a pair. And indeed, we do right here. So we'll use that to establish our ratio. Let's pull over our calculator. First thing I'm going to do is make sure I'm in the right mode, which, as usual, when I first start a lesson, I'm not. So degrees. Now we're going to determine the ratio by taking the sine of 73 and dividing it by the length of the opposite side. I didn't write it in, but I probably should up here. Whoop! Don't want to write it with that. $73 degrees right here. Pull the calculator up. We're going to take the sine of 73 degrees and divide it by 40. That will give us our law of sines ratio of 0.0239. So we've got a ratio of 0.0239, we'll say. And we want to know what A is, so how good is this? We're going to say that this ratio can be found this way. The sine of alpha over A, and of course A is the one we're looking for. So A is going to equal the sine of alpha divided by 0.02391. Let's find out what the sine of 24 degrees is. Sine of 24, 0.4067, 0.4067, and we're going to divide that by the law of sines ratio, 0.02391. 17. So A is 17 feet. Very good. 17 feet. I like the looks of that. We'll go on to another example. We've got 2 markers, A and B, on the same side of the river. So let me mark this. We'll say this is A and this is B. And they're 58 feet apart. So let's put that in. 58 feet. A third marker is located across the river at point C. A surveyor determines that the angle CAB, that's this angle right here, is 68 degrees. An angle ABC, that's this angle here, is 68 degrees. Oh, for heaven's sakes. Is that? No, that's an error on my part, isn't it? Because in your notebook, it says 52 degrees. That was a typo on my part. So I will correct it. We'll make this 52. Try not to mess things up too much. I just messed it up a little bit there. Okay, so we got 52 degrees. This is like the parting of the water. If I did that a little bit more, we'd be able to just walk across the riverbed. Okay, so we'll make this correction so it matches your sheet. What is the distance between the points A and C? So we're interested in this, and this is going to be B. Let's put together our little chart. We've got alpha equals 68 degrees. Boy, we haven't been using radians hardly at all, have we? Beta is 52 degrees. And gamma, we certainly could figure out, right? If we've got 68 on, 68 plus 52, and then the difference with 180 is 60 degrees. So our gamma is 60 degrees. A, B, and C. Which is the length that we're interested in? B. So let's mark it right here. This is the one we're trying to find. And we do have one of our lengths. We've got C. It's 58. 58 feet. So using law of sines, I can figure out the ratio for law of sines, which will be the sine of 60 degrees divided by, oh, is that right? Yeah, sine of, I should have marked it down here, I think. 60 degrees. I like to, if I'm using it, I like to put it in the diagram. The sine of 60 degrees divided by the opposite side, 58. That's my ratio for law of sines, 0.01493. So I've got 0.01493. And I'm interested in finding B, so I'm going to take the sine of beta and my unknown that I'm trying to find, B. Alright? So we'll end up saying B equals the sine of 52 degrees divided by our law of sines ratio. Sine 52 divided by 0.0149. And we get 52.8. So the distance across here is 52.8 feet. All right, so here's our answer. The question in part B is, what's the distance across the river? So what is this distance here? Now we can use right triangle trigonometry, I think. Do we know what? Yeah, we know this, so let's write it in. This was 52.8 feet here. And do I know what this angle is? If this is 68, then this will, the whole thing will add up to 90, so this one must be 22. Does that make sense? Yeah, so we got 22 degrees. Not good at this. 22 degrees right here. Let me redraw this. This is getting way too ugly looking. So I'm going to draw, I'm going to, better keep the same orientation, hadn't I? Otherwise it's going to get too confusing. So this was C, this was A, this was, here's the angle we have, which is 22 degrees. So we know what this one is, right? That'd be 68. This is 52.8 feet. So let's reorient this. I'm looking at, or I'll at least label it a little differently. This is my hypotenuse. This is my opposite. And this is my adjacent. And I want to have a calculation that includes the adjacent, and I have the hypotenuse, so clearly I'm going to be interested in using cosine of 22 degrees equal to the adjacent, which is what I want, that's the distance, divided by the hypotenuse, 2.8. Okay, so our distance equals the cosine of 22 degrees times 52.8. What's the cosine of 22 degrees? Turn this on. The cosine of 22 degrees is 0.92718. 0.92718. And we're going to multiply that times the hypotenuse, which was this distance right here, times 52.8. And it says the distance across the river is 48 point, well, actually you'd round that up, wouldn't you? So we'd say 49 feet. Distance equals 49 feet. See how much that diagram helps? And this was a multi-step problem. We first found this distance here, AC, using what we know about oblique triangles, and then we used right triangle trig to find the distance immediately across the river. Wow, nice work. Here's two problems which both use a hot air balloon. We've got a hot air balloon. We've got person A, so we're going to put person A right here. And they're looking at an angle of elevation of 25 degrees. Person B, over here, has a much steeper angle of elevation, 40 degrees, and they are 4,000 feet apart. Now, if this is 25 degrees and this is 40, what do we know about that last one? Turn this on, say 25 plus 40, and we find the difference with 180, so it's 115 degrees. So this is an obtuse angle, 115 degrees. Let's put together our little chart. We've got alpha equals 25, beta equals 40, or I should be putting the degrees in. You'll be understanding if I avoid that. It just doesn't, I'll fix that problem eventually. I actually have a call into the smartboard technician to try and help me with that. Alright, so let's call this point C. So I've got C is equal to 4,000 feet, and I've got A and B. Actually, what I want to find is the height of the balloon, H. So, but this is going to be a two-step problem, sort of like what we just did with the river. First, let's find this one. What is this length here? Of course, that will be A. So we're going to recognize this is what we want to find in our first step. And we're going to do this with law of sines. And I do have a pair. Here's my pair that I can use. All right. So, on the sine of 115 degrees divided by 4,000 is this is scientific notation. Notice we're to the -4, so we're going to move the decimal place 1, 2, 3, 4. So it's going to be 0.0002. So my ratio is look at that. 0.0002, and then 2.658. That's my ratio. And I'm interested in finding A, so I'm going to take the sine of alpha over A, and we'll find out what this length here is. A is going to equal the sine of 25 degrees divided by this ratio. It's okay if I don't write it all out at all. So the sine of 25 degrees divided by 0.123 zeros, 2.658. So this says that A is 1865.2. So I'm going to write this down over here. 1865.2 feet. So let's look at that triangle. We can use right triangle trig now. I've got 1865.2. We use right triangle trig. 1865.2. This is 40 degrees. And what I want to find is H. So that would be opposite the angle I'm interested in. I have the hypotenuse, so clearly we're going to do sine. Sine of 40 degrees equals the opposite, which is the height I'm interested in, divided by the hypotenuse. Oh, these problems are so good. They're bringing everything back, some of the stuff we haven't looked at in a little while. So the height is going to be the sine of 40 times the length of the hypotenuse. We'll pull over our calculator. See how important the calculator is to us. In my time, we didn't have calculators. Can you imagine doing this without calculators? Well, it's not like we didn't have something. We had plenty of tables and a slide rule, which you probably have no idea what that is. Someday maybe I'll show you. Okay, the sine of 40 degrees times 1865.2, and that tells us that the height is 1199 feet. 1199 feet. And we say to ourselves, does that make sense? It seems pretty reasonable, doesn't it? We'd expect it to be shorter than this length here. Yeah, I think that makes pretty good sense. All right. Now, the next example, we're going to use the same angles. So what have we got here? Let's write it in. I'll do it in green again. So we'll do A right here at 25 degrees. Let's assume the people are on the same side of the balloon. Oh, I see how that's working. So now, this person is still looking at an angle of elevation of 40, while this person is 25. The only thing that happened is we moved this person from here over to here. So that means that this would be, how many degrees? This is a straight angle, so this would be 140. If that's 140 and that's 25, then this is 15 degrees. I've got a lot of information here. Okay. So let's write it out. I've got alpha equals 25, and we're going to call this now is going to be our beta. Beta equals, this is what we're looking at right here, 140. And our gamma, we call this C up here, is equal to 15 degrees. Well, we better have some kind of a length. I think we do. Same angles and distances. So this is kind of a matter of interpretation. So if I say it's the same as up here as far as distances, then I'd have to say that this is 4,000 feet. Now I think I'm just going to wipe this out because I have decided it's probably irrelevant and wrong. So I've got the opposite side to A, I don't know. The opposite side to beta, B, I don't know. The opposite side to gamma, I do know. It's 4,000. Same problem, and now we also want to find the height of the balloon, right? So we're going to be trying to figure out what that is. So what we're going to be interested in is this right here. We'll get this length. Which length is that? That's opposite A, so we'll be looking for this. We have got a pair we can use to establish our law of sines ratio. Let's do that now. The sine of 15 degrees divided by 4,000 We know we're going to get some ridiculously small number here, right? This time, we're going to move the decimal point 5 places, so we're going to have 4 zeros in front of this 6. So that's our ratio. Let's write it down. We have 1, 2, 3, 4 zeros. Then we get 6, 4, 7, 0, 5. And we're interested in finding A, so we're going to take the sine of alpha to find A. A is going to equal the sine of alpha divided by the ratio for our law of sines. Okay, so sine of 25 degrees divided by 0.1234 zeros, 6, 4, 7, 0, 5. 6,000. Wow. Well, does that make sense? I guess it does. It would have to be longer than this. So, yeah. So we've got right here, let me put it in red. We're going to have 6531.5. 6531.5 feet. Now we're going to find the height, and we're going to use right triangle trig here. We want to know this side opposite to 40 degrees, and we have the hypotenuse, so we're going to use sine. Sine of 40 degrees equals the opposite side, which is the one we're interested in finding, we don't know what it is, divided by the hypotenuse, which we just calculated. So our hypotenuse is going to be equal to the sine times the length of the hypotenuse. Sine of 40 degrees times 6531.5. Whoops! This is not good. Wait a second. What did I forget? I didn't put in my parentheses. So easy to forget to do that. Times 6531.5. Believe me, I would have gotten the wrong answer. So it's 4,198. I'm going to round to the nearest foot. With dimensions of that size, you usually would not bother going into decimal feet. 4198. 4198 feet. All right. We have to ask ourselves, does that make sense? Does that seem reasonable? I agree. It does seem reasonable. See, how many more problems do I have? These go on and on and on. Do I ever get to an end? Not really. All right. So what I'm going to recommend here is that having done this many, these are good examples, we're going to do these in class. So probably the next two classes and your next homework are going to be around these problems, plus look at these homework problems. We have so many great applications to play around with. This is wonderful.